Okay, so now we're gonna talk about Dijkstra's algorithm, the most fundamental algorithm used to solve the shortest path problem in weighted graphs is Dijkstra's algorithm. It is a classic algorithm in computer science and serves as the foundation for many modern routing systems. Okay, Dijkstra's algorithm is based on a greedy strategy, meaning it makes the locally optimal choice at each step with the expectation of reaching a globally optimal solution. The key idea is to iteratively expand the shortest known path from the source node. The algorithm maintains a set of nodes whose shortest distance from the source is already known. The algorithm works as follows. At each step, it initializes distances, select nearest node, update neighbors, and repeat. Okay, let me now explain the pseudocode in detail. First thing, we have to initialize the distance of the source as 0, and for the all other nodes, the distance should be infinity. Then we create a priority queue and insert all the nodes into that queue. After that, we have a loop, which is while the queue is not empty, we extract node u with minimum distances. For each neighbor v of u, if the distance of u plus the weight of u and the vertex, the u and v, is less than the distance of v, then we update the distance of v to make it the shortest one. So, as we said, the algorithm maintains a priority queue in efficient implementations, which reduces time complexity to big O of v plus e log the v. Moreover, priority queue is a critical data structure that allows efficient selection of the minimum distance node. Each update operation is called a relaxation step, which improves the estimate of the shortest path. Okay. Now, let us consider a small graph and apply the algorithm step by step. We have this graph, as I showed you before, Amman, Zarqa, Irbid, and the weights between them. So first thing, we have the initial state, and that is we start by assigning the distance to the source node, which is Amman, to 0, and we make the other ones to infinity, to all other nodes. Then we have the first update, and that is from the source node, we update all neighbors. So Zarqa becomes 10 and Irbid becomes 20. After that, we choose the next node. We now choose the node with the smallest distance, okay? And with our graph here, which it is the Zarqa. So because we have 20 and 10, so we choose the smallest distance, and that is Zarqa. After that, we have the relaxation step. That is, as we see here, we have path 1, and that is from Amman to Irbid, which is 20. And we have path 2, and that is Amman to Zarqa and then to Irbid, and the total was 25. So we choose path 1 as it was shorter. We calculate a new possible path through Zarqa. Since 25 is greater than 20, so we ignore it. Okay, and then we have the final result, and that is the shortest path is from Amman to Irbid, and that was equal to 20. Therefore, the shortest path is the direct edge from Amman to Irbid. Okay, the relaxation concept. So this process is called relaxation, where we improve the shortest known distance. And here I have an example, and that was the distance before was 50. And after the new path, the distance was 30. So we update the distance to be 30. And that sums up what the relaxation concept is. Okay, complexity analysis. The efficiency of Dijkstra's algorithm depends heavily on the data structure used. So if we use an array, the time complexity will be big O of v squared. And using a binary heap or priority queue, it will be big O of v plus e log the v, where, as we said, v is number of vertices and e is the number of edges. This makes the algorithm scalable for large graphs. We have the priority queue concept, okay? So we have a queue containing Amman with distance 0, Zarqa with distance 10, and Irbid with distance 20. So first thing we do is we extract the minimum, which is Amman, and then the next minimum we have to say like Zarqa. The algorithm uses a priority queue to always select the node with the smallest distance efficiently. Okay, to sum up, the correctness of Dijkstra's algorithm relies on the fact that once a node is selected as the minimum, its shortest path is guaranteed and will not change. In the next video, we will explore how these concepts are applied in real world systems and discuss advanced challenges.